look like Matt Lauer.
I'm gonna take that. I'm gonna take it well though.
Apparently people are upset that he didn't shave.
Oh, wow. People have a lot to worry about.
I know, I mean, like what?
A lot to worry about.
Watching a little too much TV.
I mean, it's cold in Russia-ish. Might want to, well, apparently not anymore. So friends, here is what the TI has been busily doing while you guys were busily calculating. Now, you were doing what are called theoretical probabilities. In other words, you took the dice in your hands, turned them over, and figured out what all the outcomes were. That's great when you can do it. And there are only certain times when you can do that. For example, coins, dice, cards, all the things related to gambling, which is exactly how this class came to be. This class was invented, if you will, a couple hundred years ago by two guys named Pascal and Fermat. You guys heard about it in 105. They were basically gambling with each other, had to stop halfway and split a pot fairly, a pot of money fairly. One guy was one game ahead out of 10, and they had to figure out how are we going to split the pot fairly so that that likelihood of finishing the game with one of us winning or the else is weighted properly. Hence, everything we're doing right now, the idea of weighting outcomes. So, coins, cards, dice, you can turn those over in your hands and actually get all the numbers that you need. Excel is not doing that though. Excel is actually doing the experiment by rolling dice. So far it's rolled about 13,500 dice. Pairs of dice, so I guess 27,000 dice paired off in twos. Take a look at the results it's getting. Here's the results. I put percentages up top. How are these, say that again.
They're not changing.
They're not changing. Well, part of that's because the damn graphical, it's not going to change much. I'm going to lift the stapler real quick.
Oh, okay.
There. It shifted a little tiny bit. It's not updating real time.
Okay, got it.
Unfortunately, I don't know why that is. Certain computers on campus will and certain ones won't. So what is changing real time are these in here. The non-graphical part is changing very quickly. The little red one that you're seeing bouncing around is the current roll that's being counted at that moment. And then it moves on. Notice how frequently we're getting ones in this middle region, but how rarely we're getting ones out here. Oh, there we go. On average, we're going to get one every, on average every 36 rolls. That is not a promise, as we learned last time, right? It's not a promise that every 36 rolls you get a snake eyes. Otherwise, that'd be predictably blocking every 36. But what's happening is over time, we're getting one. And the over time part is this column. The probabilities that are keeping track. These are the same numbers you got, aren't they? What's 1 in 36 as a decimal? What's 1 in 36 as a decimal? If you type in 1 in 36 and press enter, what do you get?
0.03.
Roughly point, it rounds. It's not exact, but it's 3%, rounded to 100th place, right? It's 3%. This should be about twice as big, 6%. This guy right here, now notice, why isn't that 9%? This should be 3 times as big as that, it should be 3 times as big as that. You gotta remember that this isn't exactly 3%, it's a little shy, isn't it?
Right.
It's a teeny bit shy, but it rounds to 3%.
Right.
This one rounds to 8%. But there's 1 in 36, there's 2 in 36, 3 in 36, 4 in 36, 5 in 36, 6 in 36 is 0.166666667, rounding to 17%, and then it starts waltzing back down again. Meanwhile, the dice are behaving individually exactly as they're supposed to, which means over time, the sums are going to behave exactly as they're supposed to. This does not guarantee that we won't get a run of snake eyes or boxcars. I guess we're not getting one right now.
You just missed one.
Turn around, damn it! And that's the idea. That's why you have to laugh at people sitting in Vegas waiting for the little old lady to get up out of her chair. You gotta laugh at them because they're doing the same. I'm doing it facetiously, they're doing it seriously. That machine is due. That machine is due. That machine is about as due as this spreadsheet. Stop right there, sit down. Oh, I would have won! You see? I turn around. At that moment, he got a 1. But you can't bank on that. It's not a promise. It's a probability. It's a long run average. And so, I laugh about it because it breaks my heart to walk through casinos and see that. When I go to Vegas, I go to the rock climb. Wonderful rock climbing down there. But I have to go to the casinos. A, because I love inhaling secondhand smoke. Love it. But B, because I just love watching these people and their theories they have about how they're going to crack the system. You're not going to crack the system. They have the lights on 24/7. They are piping water in from Los Angeles because you are giving them money to do so. How are you giving them money to do so? They understand this.
But there's books that tell us how to win.
They do. Games of skill, yes. Poker, blackjack, those you can actually win the games. A one-armed bandit is pure chance. You can't beat it. Unless, the only way you can beat it is it's calibrated wrong. But guaranteed, it won't be calibrated wrong. They make sure it's not calibrated
Like in
wrong.
casino.
But the casinos, that's why I say they. The casinos make sure it's not calibrated.
No, go back to the movie Casino.
Oh, go back to the movie Casino, exactly. Checking the weights. That one scene that his brother-in-law, whatever it was,
Yeah.
is that the cousin something
Something happened.
his job was to calibrate. He was doing it poorly, paying out too much. Too
But
loose.
he's like, you're either cheating or you're too stupid and you don't belong here.
Exactly. Loosest slots in Vegas. That's the phrase they often use. Loose, as if they're going to pay out more. Now, granted, they might adjust them to pay out more occasionally. They might, but they're never going to adjust them to pay out so much to make their average. Well, we'll come back to that. I'm getting ahead of myself a little bit. That's the next experiment we'll run, which is called Chuck-a-Luck. So anyway, I think we're happy with this distribution. Let's see if it changes any. I think we're pretty much settled in now. Throwing staplers. So we're good. There's our distribution. Next up, please give me an average and a standard deviation of this distribution. Use your TIs. I'm not going to make you do this one by hand. It's too much of a pain in the butt. Use your TIs. There's your distribution. Give me an average and a standard deviation. Go ahead and run your